Computer. Good morning, Organic Chemistry 2330. We're going to continue on our educational journey through yet another difficult time. Okay. Charles Darwin, you might think of saying survival of the fittest. Well, that's not exactly what he said. He said those who survive are the ones who are willing to adapt. So we've adapted once for COVID, and we're going to adapt for this as well. So I want to reach out and say, let's keep going. Let's move forward. If you are having issues and troubles trying to do this, I personally reached out for help this week, and I encourage you to do so if you need it. There are services both at the university and online. Call a friend, just vent, go ahead and get into a great mental place where we can finish this semester strong, okay? So that being said, is there any questions about the new schedule? Notice our homework is due on Monday, the March 1st, so that we can have it for review. I will be giving a review, and there's already a review set of slides on Canvas if you want to start reviewing. It's review exam 1, chapters 1 through 7. Go ahead and start that and try to figure out what you do and do not know very well, and so that you can do that. And then I will go over some of the other things. In addition, if you want to make sure you have what you want for the important topics, on Top Hat, there are a set of slides called 3 goals. And look at those 3 goals, because each of those goals is a major issue that you need, and it has explanations of those goals. So go ahead and make sure that those are really good concepts in your head. And those goal slides will give you a place to start as far as making sure that you have the concepts correct, and then you can build on that with this homework. Okay? Questions on that? Excuse me. Already hitting the green tea. Okay, so with that, if there are no questions yet, I will go ahead and start with slides for chapter 6. All right, share on my screen. And let's see, where did everybody go? Okay, there we are. Going to do gallery mode. I'm moving up the people on video over here. All right, is the slide still on the screen? Okay, yes. Sometimes when I move it, it changes. All right, so this topic here is very interesting, and it has everything to do with the idea that when we were drawing these structures, we had little wedges that were solid or they were dashed to help you get that 3D space. Well, it turns out when you have 4 different things bonded to a carbon, it gives it a special thing called chirality. Okay, so chirality just means you have 4 different things bonded to carbon, and to name it properly, we have to use a system for this called the Rns system. So I'm going to go through each of these things in detail and teach you how to use your hand and or that kind of concept to correctly assign RNS. And then in addition to that, I'll email out a practice sheet and a key so that you can see if you have the concept down. All right, so with all the other things we've talked about, you can hook carbons up different ways, and we have different kinds of isomers. So if they have the same molecular formula, they're hooked up differently. Those would be, those would be constitutional isomers. They're just different connections. Okay. However, if they're different only in their orientation in space, okay, then we call those stereoisomers. Okay, stereo meaning space, isomers meaning isomers. So when we think about that, we have to think that, okay, I have something like my hand here, and it looks almost like my other hand. So the fingers are in about the same places and the thumbs are about the same places, okay? But they are completely different in space because they aren't exactly the same. And so we think about those things, if all of these were just atoms, those atoms we hook differently in space. And that's what we mean by stereoisomer, okay? Within stereoisomers, we have 2 types. We have what we call enantiomers, which is a pair, it's only 2. It's a pair of 2 molecules that are exactly the same, except they have non-superimposable mirror images. And I'll talk about that in a minute. What that means is kind of like a hand where they look identical to each other. And if you put your hand on the mirror, it looks exactly like the other hand here. But if you tried to make them sit on top of each other, the thumb and the finger would overlap, and you could never arrange them so they were completely overlapping. And that's what we mean by non-superimposable mirror images. Now, if you have more than one stereocenter, then you can have what we call diastereomers. And you can think about that as, di meaning two, so two or more stereocenters, and you have diastereomers. And those go into a set of different isomers that are only different by their position in space, okay? So I'm gonna go through each of these and tell you how to assign the correct nomenclature to each of these in today's lecture. Okay, so I said before, an enantiomer is a non-superimposable image, okay? And so what we will do that is if you draw a molecule and then you imagine a mirror plane here and you draw it on the other side, now when you try to take those two molecules and overlap them, they will not overlap because in the case of this particular structure here, if we tried to, let's go to red, make this group line up with this group over here, what we'd end up with is this hydrogen would be overlapping with this methyl group and this methyl group would be overlapping with the hydrogen. We can always get 3 of those atoms connected, including the central carbon, to line up, but then the other 2 groups are swapped, okay? So that's what we mean by a non-superimposable mirror image. Okay. So how do we see that? Well, let's take that molecule we draw right here. And if we want to, do it by hand, what we would do is we draw our molecule, and I'm just going to do it right here. 1, 2. A big wedge right here means it's coming out of the page. A dash wedge means it's going into the page. I'm going to do a 1, 2, 3, and a 4. Okay. So the way we know we have our mirror image is we actually make a mirror, and we start with the atom closest to the mirror and say, okay, that's 4, and that's a wedge, a dashed wedge. Then we have 1 up here. We have a 3 down here, and we have our 2 over here, okay? So that's how we draw our superimposable mirror image, okay? Now, if we take that superimposable mirror image and try to line up these 2s, what we're gonna do is we're gonna rotate it 180 degrees, okay? So in the picture down below, we're gonna take that mirror image of this butanol, 2-butanol, and we're gonna rotate it around that by 180 degrees. So we're treating this methyl group to rotate to it lines up with this methyl group here. Okay. When we do that, we can see that the ethyl group now is on the behind the plane because it has the dash wedge. The hydrogen is in front of the plane because it has the solid wedge. So it is those 2 groups have swapped positions in space. Okay. So because those 2 groups swapped positions in space, we now have a pair of enantiomers. One enantiomer is one configuration, the other enantiomer is the other configuration. We always have a pair of enantiomers, okay? Questions on that? Okay, we're gonna do this manipulation. This rotation around an axis, one axis or sometimes 2, is where love of Minecraft would come in because you have to do all the rotations to get everything built right. Being able to rotate that in your head or draw it on paper is a valuable skill when we're talking about chirality. Okay, so when we do that manipulation where we take an image, we make the mirror image, and then we rotate it around so that it tries to fit on top, we saw that we have 2 groups specifically that swap places. Okay, notice that these groups right here all would line up. This alcohol, the OH, the carbon, and the methyl group all line up because they're all still in the plane of the paper. But the 2 other groups have swapped positions. Okay, that's the telltale sign we have our pair of enantiomers. Okay, notice everything else is exactly the same. We've drawn it as the mirror image, but now once we rotate them, they do not superimpose. So that means that they are that enantiomers, and they have different properties, specifically the way they interact with light. okay? If they were different compounds or hooked up a different way, then that would just be an isomer. That wouldn't be an enantiomer. Okay. So the whole concept here is that it was decided that, it was related to handedness. So in the case of our Greek starting point of care, it's shown that they are handedness, so that one would look kind of like this. Your tetrahedral carbon would look kind of like this, and your other tetrahedral carbon would be the opposite of it. Okay, and so this only works if there's 4 different groups bonded to carbon. So if you go to a molecule and they say, "Oh, is this molecule does it have an enantiomer?" Well, the first thing you're going to do is say, "Okay, does any of the carbons have 4 different groups attached to it?" If it does, that means it has what we call a stereo center. That means it's a different center in space. Okay, but there has to be 4 different groups. Okay, if you have 2 methyl groups, a hydrogen, and a chlorine, that will not have a stereo center because those 2 methyl groups would be superimposable on each other. So you have to have a methyl group, an ethyl group, a hydrogen, and a chlorine, 4 different things to make that stereo center or that chiral carbon. Okay, so the term chiral means handedness, and sometimes it's the chiral carbon or stereo center or stereo carbon. They all mean the same thing. It's that the carbon that all 4 different things are built on. Okay, now, if you, let's say you have something that doesn't have those 4 different groups, we call that achiral or not chiral. So the example here is like when we have those 2 methyl groups. If we do the 2 methyl groups right here, when we make the mirror image, we can actually rotate that around so the 2 methyl groups overlap on each other, and therefore it is superimposable, and therefore it is not a chiral compound, so it is an achiral compound. Okay, so achiral and achiral carbon are 2 different things. So achiral means you have no center, and stereo center carbon, or I'll try to make sure that I don't use the preposition a in front of chiral when I'm talking about a chiral center. Okay, so and the whole reason that we can call these achiral is because we can do that rotation. We can make them overlap each other, and therefore they don't follow the definition of handedness, being non-superimposable. Okay, so what that means is if you have an object that is a non-superimposable mirror image, it can be chiral. Oh, it is chiral, sorry, it is chiral. It shows that they are different, just like the hands would be, okay? Most commonly, the chiral among organic compounds are on the carbon with 4 different groups. However, you can have 4 groups on nitrogen sometimes, and those can also be chiral. The carbon must have 4 different groups bonded to that stereo center. The carbon in the middle that has the 4 different groups is the stereo center, because that's where you're going to do all your rotations. If the object is superimposable with an image, it is not chiral. It is achiral. Okay? And non-superimposable images are a pair of enantiomers, and like gloves, they always come in pairs. All right, questions on that? So that's just, go ahead.
Can you go over again what it means to be non-superposable?
Okay, for non-superimposable, it would be, so let's say this is my mirror image of this, right? And so if I tried to line up my index fingers and my hands together right here, notice that my thumb and finger are overlapping and my other thumb and other finger. So I can't ever line it up so that my thumbs, so that all the 4 different groups line up. I'll always be able to get 3 atoms to line up, but then the other 2 are going to be swapped. That's what non-superimposable means. Does that help?
Yes, thank you.
So that trying to get that in your head so that that it's at least 2 groups are not in the exact same place. That is the point. Okay. All right. So when we draw chiral carbon molecules, we try to make sure we show all the 4 groups, and we use wedges. Okay. We can do it where in most cases we actually usually leave the hydrogen off right here, but I feel it's better if we draw it with the hydrogen there to make sure you don't forget it. Okay. So there's a couple different ways to do it. Whenever we draw these molecules, we're going to have 3 atoms that are going to be in the plane of the paper. Okay, so those are going to be the ones with just the regular sticks for the bonds right here. And then we're going to have something that goes behind the plane of the paper and something that's in front of the plane of the paper. So this is behind with the dash wedge, and this is in front with the solid wedge. And it doesn't matter how you draw it. You can draw it, like this is kind of upside down. You can even do this figure here. I would avoid this one because you might forget that hydrogen's there, and you need to know where that hydrogen is to help you know where it is. Okay. So I would avoid this one because you have to remember to put the hydrogen there. Okay. So when you're drawing these, draw them with the wedges and the sticks. Okay. Okay. So how do we convert from one to the other? Well, if you have an enantiomer like this, the easiest way to do it is to make it where you draw a mirror and then you transpose it. So you put an imaginary mirror right here in the middle, and then you have a line there, and well, this one's going in, yeah, this one, no, this is a representative of the exact same compound, so that's not a mirror. Okay, so that's not where our mirror goes. Our mirror goes here. Sorry, here. All right. So notice that this is the closest one, then that's the next closest one, and that's the next closest one, and then we have a wedge and a wedge and this right here. So that means this is the mirror image of this. But if we were to rotate this part around 180 degrees, right? So the hydrogen that was behind comes forward and the OH that was in front goes back, we end up with this representation. So notice how the only group that's switched is this OH group and of course the imaginary hydrogen. So we've had 2 groups switch locations. All the other atoms stayed in that same plane. Notice they're all in the same orientation. Only the OH and the imaginary hydrogen have swapped positions. So that's the way to make sure we know we have a true enantiomer mirror image. Okay. So now that we know they're different compounds because they're going to interact with light differently, we have to learn how to name them correctly. Okay, they're different in space, so they are different chemical compounds. And an example of this is ibuprofen. Ibuprofen has carboxylic acid on this little thing here. It's an anti-inflammatory, NSAID, a non-steroidal anti-inflammatory thing. But if you made it and you made both isomers just from whatever reaction you use, only one of the isomers is actually biologically active. This is the one that does the anti-inflammatory agent. This is actually not active at all and would be unuseful to have it in your system. So we have to, number one, know which one is active and not. And most pharmaceuticals are specific to one or the other. And we need to know how to name which one. And with that, we have what we call the Rns system. Now, if you look back onto Canvas, there is a thing about nomenclature, and the Rns system is on that nomenclature review session, and so that you can get these rules from that as well. But I wanted to draw your attention to that resource for you on Canvas. Okay, so we have Rns. So let's talk about Rns. What does Rns mean? Okay, first of all, because it was Greek and they said handedness, okay, they determined it was going to be right hand and left hand, okay? So in the case of the right hand in Latin, it's rectus, meaning straight and correct, or the opposite would be S, or sinister, or left, or incorrect. So the idea here is that when we assign these, we're going to have one assigned as an R, and I'll talk about that in a minute, and then one assigned as an S. So we're always going to have, if you draw both enantiomers, one's going to be R and the other has to be S. Okay, so the first thing we're going to do is we're going to assign the priority from 1 to 4. Okay, we're going to use the exact same priority rules we used for assigning E and Z. So we're going to start with atomic number, So the highest atomic number is always the highest. And then if they're the same, we look for the things attached to it. And then if we have to go out multiple bonds, we use those. So we're going to use those same rules of priority, but we're going to assign all 4 substituents on that carbon in the middle. Okay, we have to assign all 4. We don't have to just assign one side or the other. We have to do all 4 in order. Okay, now what we're going to do is we're going to, after we assign that order, we're going to make that stereo center of the group, the lowest priority is pointing away from you. And that's where your hand comes in. Okay, so if we're going to do a stereo center, you always have your wrist as the stereo center because you can look down your hand and assign 1, 2, 3, and then 4 is always back here. That gives you the position to know which way is clockwise and which way is counterclockwise. Okay, so let's say we're looking down my hand here, and this is 1, this is 2, this is 3, and a 4 is back here. Okay, so 1, 2, 3, that is going counterclockwise. Okay, counterclockwise. Just want to make sure. That means this is the S configuration. Okay, because it's going counterclockwise, and our lowest priority group is in the back. So let's go ahead and look at its enantiomer here. We're going to do that same assignment. We're going to do 1, 2, 3. My thumb is 3. So that's going now clockwise. So that would make this the R configuration or the clockwise configuration. Okay, so in that assignment, this hand is S and this hand is R, which of course is backwards, but there you go. Okay, questions on that? Don't worry, we're going to get a couple. I see a hand up.
I have a question about the last slide, actually. For the active one, if that methyl and hydrogen switched, which was going back and forward, would it still be an active form?
Well, if they switch, it'd actually be this one right here. And this is, if you just switch those 2 groups, notice that this is just that molecule that's been rotated around. And so if this methyl group is actually in the back if we oriented it this way. So this is the other enantiomer.
How come the lines are the same then for the hydrogen and the methyl? Like both of the hydrogens show going behind.
Okay, but notice that this is going, this part and this part are in the plane of the paper, but they've swapped positions here. So what we're showing here is that these 2 groups have swapped positions. This one is now over here for this one, and this one is now over here for this one. So really, they kept the methyl group and the hydrogen the same. They swapped the other 2 groups in the picture.
Okay.
Okay, so yes, you're right. The methyl group and the hydrogen did not move, but they moved the other 2 groups in this example. All right. Okay, so let's go and do some practice with RNS here. And what we're going to do is we're going to do our priority. So our prioritization is by atomic number first. And so if we look at that right here, chlorine is going to be 1 because it's bigger than carbon. Then we have a choice between this carbon and this carbon. This carbon has 3 hydrogens on it. This carbon has 2 hydrogens and a carbon, which gives this a higher priority than this one. And of course, our hydrogen, which is usually the last, is always 4. Okay, so now that we have that, let's try to get our hand on this such that we can do it. So just looking at this structure here, we're going to set up our hand, put our hydrogen way back here, and 1 is our chlorine, that's 1 pointing up at us. 2 is going to be our index finger, and 3 is going to be the thumb. And so that is going 1, 2, 3, 1, 2, 3 counterclockwise, which makes it N what? Huh?
S configuration?
S, that is correct. Yes. So see how I did it where I made sure I assigned priority. I put the lowest priority on the back, and then I looked for the counterclockwise and the clockwise. Okay. So let's do the next one. It's a little bit harder. Okay. So we have our oxygen is our number 1, of course, because it's higher than carbon. And this carbon right here is our number 2 because of our 3rd rule of priority. Our priority said that if you're bonded to If you're double bonded to carbon, it counts as being bonded to 2 carbons and a hydrogen, and this is only bonded to 1 carbon and 2 hydrogens. So that's why this one takes priority. So now let's do it again. We're going to do it again. Notice I kind of drew it easier because the hydrogen's in the back here. So the index finger is 1, my thumb is now 2, and my my middle finger is 3. So that's going clockwise. So that's going to give us our R configuration. Okay. Questions on being able to translate to your hand to find clockwise versus counterclockwise? Okay. So that's the easiest method I found because I usually take my hands everywhere. And so I don't need to actually like have a book or anything. So that's what I kind of do. Some people actually do the drawing and rotate and all that, and that's fine. And that's actually one of the things that he does on my chemistry tutor. So if you don't like the hand thing, you can try his configuration and he'll lead you through his process. All right. All right. So let's go back to that ibuprofen and show you why we have them in those different ways. Even though they're drawn similarly, we can show you why that they are enantiomers of each other. So when we look at priority here, this has our first priority because we have that carbon has an oxygen double bonded to an oxygen, to this double bonded to it, plus another oxygen. So this has 3 oxygens bound to it. This has 3 hydrogens bound to it. And this one right here has 1 carbon for this, 1 carbon for this bond, and 1 carbon for this bond. So that's 3 carbons bound to this carbon here. Notice I'm only prioritizing the atoms directly attached to the middle here. Okay. You only assign priority to those things because once you've assigned priority to those, you are done. Okay. So now let's go ahead and assign this right here, trying to get it closest. So my index finger, I'm going to put as the methyl group. I'm going to put my thumb as the carboxylic acid, and this is the benzene ring or that alkene. And that gives us 1, 2, 3. And so that is going clockwise, which is our R configuration. Excuse me.
You said number 2 has 2 carbons, correct?
Number 2 has a total of 3 carbons because 1 carbon is for the first bond, 1 carbon's for the second bond, and 1 carbon's for this one over here. So it technically has 3 carbons bound to it by our prioritization rules.
So does the R and S configuration determine the activeness of the compound?
Yes and no. Your body can only use one or the other. It typically can't use both. And I have an explanation for that later in the slide, later in the slides. Okay. But usually because our bodies are very complex and there's lots of chiral molecules out there, they tend to only use one of the isomers and not the other, or the other isomer is actually bad for you because it does a different biological process. So. Oh.
Right. So my question was more or less like, does the R, so it says R for ibuprofen is the inactive. Is R always inactive?
No.
Or
it's specific to the drug. It's specific to the biological system. For example, we can like process an S isomer of something, and your dog will process the R. So of the same compound. So it's independent to the biological systems.
Okay, and, thank you.
Yeah. Some things like, for example, like the R can affect the brain, and the S can affect the liver. So it depends on how it's used in the body. So neither one is always right or always wrong, but it depends.
So the So the COOH takes priority because it has 3 oxygens attached to it.
Correct. Because remember, if we draw that out, the structure, you have this right here, and by our number 3 prioritization rule, we count this is 1 bond to oxygen, that's 1 bond to oxygen, and that's 1 bond to oxygen. So it has 3 oxygens bound to it. by the prioritization rules. It technically only has 2 on it, but we count each of those bonds to oxygen. Does that make sense?
I just wonder why that takes priority over the 3 carbons.
Oxygen has a higher atomic number.
Okay, thank you.
Okay, so it's always atomic number first, and then, you know, if you have to differentiate, then you continue out until there is a differentiation. And when you have double bonds, you have to count each of the bonds toward your prioritization. All right. So before I move on, let me go ahead and draw one for you. And I want you to try to figure out what it is. And what I'm going to do is I'm just going to draw it right here like this. And I'm going to be mean. I'm going to put the hydrogen here. And I'm going to put, that'll be our number 4 group here. I'm going to go 1, 2, and 3. Okay. So I would like you to, using whatever method you want, try to tell me whether this compound I just drew is R or S.
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 Yes, that is correct. Okay. If you got that right, that's great. If you don't, go ahead and go back and try that rule again. Try to be able to find the R and S. Again, it's rotating it around so that lowest priority is away from you so you can get clockwise and counterclockwise correct. Okay? Okay, so that's the R and S. And so in the homework, I think they have you do like at least a couple of these. And so they're really good to know.
Could you go over one more time how you go about labeling your hand? Like,
oh, yeah, okay. So let's we'll just pull up this here. Okay, so let's say we have, let's do this one again. That's a solid wedge. This is a, and we go 1, 2, 3, and 4. Okay, so what I do is I always put 4 on my wrist. So that's the lowest priority, so that I can look at these 3 fingers. And then in this case here, the 3 is sticking out at me. My thumb is sticking closest to me. So I'm going to assign 3 to my thumb. The 1 is sticking up. So I'm going to assign the index finger to 1. And then the 2 is also in that same plane. I'm going to do that with the middle finger here. And that's how I assign the numbers to my hand. And now that they're assigned, I can do 1, 2, 3. We have a counterclockwise. And so therefore that compound would be an S. Does that make sense?
yes, it does.
Great.
Thanks.
So yeah, that is important to be able to assign the fingers correctly. So that's good.
Just to clarify something, you're using your right hand, right? So the thumb can be facing towards you.
Uh-huh.
Okay, awesome. Thank you.
Well, but you can use it with your left hand because my thumb is still facing toward me. So if I did that exact same assignment there, I would, with my left hand, I put the 4 back here. The 3 is now sticking out at me. So that's my middle finger. The 1 is sticking up and my thumb is now the 2. However, when I look at it, it's 1, 2, 3. It's still counterclockwise. You can use either hand. It doesn't matter. As long as you put your lowest priority here and you assign the thing closest to you as the thing sticking out, you can do it.
Okay, awesome. Thank you.
All right, good questions. Okay, so that's how if we had one stereo center, okay? What if we have more than one stereo center? Things get a little more complicated. So the idea is that if you only have one stereo center, you only have 2 possible stereoisomers, the R and the S, okay? If you have 2 stereo centers, that means each of those stereo centers has 2 possible configurations. And so it's going to be 2 to the 2 power. So that means there should be 4 stereoisomers possible if you have 2 stereo centers. Now, if you have more than 2 stereo centers, it's going to be 2 to that power of stereo centers. So if you had 3 stereo centers, it'd be 2 cubed, which would be 8, and et cetera, et cetera. So things get really complicated really quickly when you have multiple stereo centers. Okay. Luckily, most biological systems only make 1 isomer, or maybe 2. And so that it makes it, even though you have 5 stereo centers in a system, and that gives you hundreds of possibilities, the biological system tends to only make one of them. So let's talk about the simplest side when you have two stereocenters, okay? So when you have two stereocenters, we're going to look at each of them differently. We can assign each of the stereocenters as R or S, okay? But now we have to figure out how to get the other pair, okay? So let's start with this compound here. This is a trihydroxy butanal. And so that is an aldehyde with three alcohols on it. And let's draw it up here. So if we draw it in this particular configuration, this configuration makes it easier to see that it is done. Notice that we still have the wedges and stuff, but our two stereocenters are in the plane of the paper and all the substituents are up or down. Now, in this particular type of drawing, we always want the substituents that are up, oops, let me erase that, that are pointing out to the sides are always solid wedges, and the two, one at the top and the one at the bottom are always dashed wedges, meaning they're below the plane of the paper, okay? So using our rule about non-superimposable mirror image, to create the other isomer, we would just create our mirror right here and start at the side. So H to OH to C to H to OH to C to H, and then this matches that and this matches that. So that's how we would draw the mirror, okay? Now notice the wedges stay the same. We haven't changed where the wedges are in that mirror image, okay? So we have correctly assigned this as our non-superimposable mirror image, which means that this is one pair of enantiomers, okay? Okay, so where does the other isomer come from? Well, so in this case here, we have one is going to be R and one's going to be S, and then this one's going to swap, so the R was going to become S and the S is going to become R. But we can also have it to where on this side, this can be an R and an R. Where's the, so for example, let's see, this is going to be, actually, let me assign it real quick. 1, 2, 3, 1, 2, 3, that is R. So yeah, this is R and this is S, which makes when our mirror image, this is going to be S and this is going to be R. But over here, we have R and R and S and S. That's how we get the other isomer. But notice, these have the equal and opposite centers on each of these carbons. These have the same center, the same assignment on that molecule, and its mirror image has the same the opposite assignment on those two. That's where the other isomer comes from, okay? Now, this pair is not superimposable with that pair, so that makes this a pair of enantiomers, but not with these. This is a pair of enantiomers, okay? And the two pairs together are what we call a diastereomer. We have two pairs of enantiomers, okay? Do we see why when we have those two stereocenters, we can have 4 different possible isomers? Okay, all right, so when we have that, we need to assign them all like that. Now, we have a compound here that is nice. It has a pair of enantiomers, and this one over here has a non-superimposable mirror image, so it is a pair of enantiomers. Okay, that doesn't always happen. What can happen is that you can get your pair of enantiomers here, swap one of the chiral centers to get to the other set, and the other set might not have a non-superimposable mirror image, and it becomes a chiral. We call these compounds meso compounds, okay? So the best way to look for that is to look for things that have these mirror image planes. So an example is tartaric acid, okay? So in tartaric acid, we have this carboxylic acid group at each end. Notice they're facing down. So the longest carbon chain is always up and down. And then our substituents are here. And so this has a nice mirror image. And these mirror images are non-superimposable. If you rotated this around to make it look like the other one, it actually, the oxygens have swapped, the OHs have swapped. So this is a true pair of enantiomers here, okay? Now, to make the diastereomers, we'd have to swap one or the other of these centers. So we'd have to take one of the centers and switch it around. So if we swap that to this side, I'm sorry, let's do it the other way. If we swapped this to this side, we would get our other isomer, but it's not an enantiomer because it's not a stereo image, but it has the other isomer available to us. But when we do the mirror image of it, the mirror image can be rotated 180 degrees and it's superimposable. Because it's superimposable, it has a superimposable mirror image. It is not chiral, it is achiral. And that becomes what we call a meso compound. It's still part of the diastereomers, but it is not a chiral molecule itself. Okay, questions on that? All right, so that is just a definition. So sometimes you'll have to draw it and then kind of see if it superimposes. If it does, it's a meso compound. And so in this case, we actually have 3 stereoisomers for this compound, not 4. All right, and the way to look for this is what we call planes of symmetry. So you want to basically slice through the molecule in a bunch of different ways. And if the same on one molecule is the same on the other, so that mirror plane is the exact opposite of it on the other side, it is going to be achiral, okay? So let's take the example of this isopropanol here. So again, the first thing we should notice is that this carbon here only has 3 different groups, so we don't think it's chiral. And the reason we can also do that is if we drew a plane through the middle of the oxygen, the hydrogen, and the central carbon, these 2 methyl groups mirror each other. That's where its plane of symmetry exists, and that's why it is not a chiral compound. So when they were first figuring this out, they figured out that it had to be 4 different groups. If you have 4 different groups, the mirror image cannot look like the other side because at least 2 of the things will be different. Okay, so let's take that and add it a little thing to make it into cyclic compounds. So the same rule applies for stereocenters. If you have 2 stereocenters, you're going to have 2 to the 2 power of stereoisomers possible. So, but we still have to draw them all and see if one of them might be a meso compound or not. Okay. So the first way to do that, if we were going to do that, is we would take our first compound, draw a mirror, and notice we can make the mirror image of it over here. The wedges are the same, and then the other half is the same. So this is our first pair right here. And notice the OH and the methyl group are on the same side of the ring, making it the cis isomer of the 2-methyl cyclohexanol. Okay, so to find the other set right here, we have to swap one of those chiral centers. So in this case, we're going to swap the oxygen here to switch it to the backside. That means it is now not the exact same isomer. It's not a mirror image of it anymore because we changed it. And notice we have the oxygen back on the bottom of the ring. We have the methyl on the top of the ring, which turns it into the trans methyl cyclohexanol, okay, because they're on the opposite sides of the ring again. And when we draw our mirror plane of that, we have this on this side and this side. Notice that we have our centers here are not the same as these. So we have our clear pair of enantiomers here. We have a separate pair of enantiomers here, giving us our set of 4 diastereomers. Okay, and if we try to rotate these around or find a mirror plane, we can't find one. But what if we could? That would make one of the molecules not. So things like that have the same group, even though they might have a stereocenter, we might be able to find a plane of symmetry. Okay, so let's take this 1,2-cyclopentadiol first. Okay, so we can If it's in this configuration here, we can draw our mirror image back and forth. And these are non-superimposable because if we rotated this around, right here, the OH would be down on this side and it would be up on this side. So we have a true pair of enantiomers on this side here. Okay, so to get to our other pair of enantiomers possible, we have to switch one of those stereocenters. So in this case, we're going to switch this OH here and switch it to the same side. Okay, now we can draw our mirror image, and so that would be our mirror image of it. Okay, but notice because we have this plane of symmetry in the middle, notice it's cutting through a bond and an atom. It can be anywhere inside the molecule. If we just rotate this molecule 180 degrees, it's exactly the same. Okay, so that's where the Minecraft thing comes in. So you could, if you rotate it around and they overlap again, you again have a non-chiral system, and therefore that compound is a meso compound. And we only have 3 diastereomers. Okay, let's see. 27. All right. Good on time too. All right. So in that case, we found a mirror image in a bond and an atom. You can also find it inside of atoms as well. For example, if you have things that are symmetrical, for example, notice they're both on, they're different groups, but they're on the opposite ends of that cyclohexane. That means we can find a mirror plane inside there. And when we find that mirror plane inside there, it makes it achiral. Now, interestingly enough, both the cis and trans version of this have planes of symmetry, and both of them are achiral, even though they have 2 stereocenters each. They are both achiral systems because of that plane of symmetry. Okay. Questions? Okay. All right. So it's a lot harder to get this to overlap like that when you have 2 different groups or if they're not symmetrically associated around a ring. So in this particular case, we are looking for all of them because we are not going to find a mirror plane. Because if we try to put a mirror plane here, the methyl group and the oxygen are different groups. If we put the methyl plane, if we put the plane in the plane of the cyclohexane here, the oxygen's up or the oxygen's down. So we do not find any plane of symmetry here. So to find our first set, we have the wedges all the same, all in this case up. And then to get the other set, we take one of those, flip it to the other side. In this case, we're using the methyl group. And we're making that mirror image. And now because they're 2 different groups, they can't be superimposable. And therefore we have our second pair of enantiomers. Okay. Let's see, I think that's all right. So, and when we change the isomer to this isomer, the 1,2 isomer versus the 1,3 isomer we had before, we again lose that plane of symmetry. We can't draw it here because our groups are above and below, are different. And when we rotate it around, the methyl CH3 comes up here and the OH comes here. So we definitely have our pair of enantiomers. And again, when we swap one of the groups to from a solid wedge to a dash wedge, we can find the other pair of enantiomers. Okay. So, all right, so let's figure out 1,3 cyclohexane diol. Okay, so what I'm going to do is I'm actually going to go to my blank page and we're going to do that separately. 1,3 cyclodiol blank for iPad. All right, so we want to do 1,3 cyclohexane diol. All right, so let's draw 1,3 cyclohexane diol. Okay, we got a cyclohexane here. We arbitrarily choose one of the alcohol, the OHs. So that makes this 1, 2, and 3. So that means our other one's going to be over here. Okay, so we've drawn our compound based on what we have, and this is all the information we have. And we want to find out how many isomers we have. Okay, I'm going to make it easier to draw the mirror image of it by doing this. OH, OH, right here. And of course, we're going to draw our imaginary mirror here. And we're going to continue drawing our sum. So H, O, solid wedge, carbon coming toward you, carbon going away, solid wedge, OH, right here. So that's one of our systems, okay? All right, so let's swap one of those and draw the other set of diastereomers. So the one we're going to swap is, we're going to swap this one right here. So we're going to draw that over here. And we're going to have a dashed wedge for the OH here, and we're going to have a solid wedge for the OH here. And for its complement, we're going to draw it over here, HO. Oops. Okay, it's not, okay. And then that's our dashed wedge, and then this is our solid wedge, OH. All right, so now we've drawn all 4 isomers possible, but we need to figure out whether they are chiral or achiral at this point. So if we take this compound here and rotate it 180 degrees, we have an OH here and an OH here. They are superimposable mirror images, okay? Which means this is not a pair of diastereomers, it is a meso compound, okay? Let's do the thing to the other one, okay? Let's rotate this around here. If we do that same rotation, we get that going, oh, okay, no, that won't work because our OH is going to be up and this OH is going to be down. So rotation doesn't work. But what if we flip the molecule from the page, flipped it over? This upside OH is going to end up being a downside. And this downside is going to end up being an upside. And if we rotate that, it now looks like it overlaps. But does it? Back one. There we go. So let's look at that right here. So when we draw those, we see that one of them does have that mirror plane. The one with the 2 wedges facing up is a meso compound, but the other 2, no matter which way you manipulate it, has the pair of enantiomers. Okay, so I showed you how to draw and how to manipulate to get to see if you have the meso compound or not. Right, questions on that?
I have a question.
Yes.
Would that be for any compound with dashed wedges and a solid wedge? It will never be meso?
No, not necessarily true. If you have a different isomer, you can actually rotate it. Like if you have the 4 isomer here, an up and down, those are meso also. So it's not just having up or down or both up or both down. You actually either one. So we just have to identify each one.
Okay. I guess I don't understand why those 2 aren't meso and the other one is.
Okay, so if we rotated this around, if we just did a rotation here, this OH would be up here and down. This would be down and lined up with this one, and this one would be up. So that we can't just do a rotation. If we flipped the molecule over on this axis here, that would be down and this would be up. And so that would be opposite of that. If we flip the molecule and rotate it around, they would still be opposite. So no matter how we moved this molecule here, it is non-superimposable.
Okay, so it has to do with what side of the cyclo it's on.
Correct.
Okay, thank you.
So some isomers, like the 1,2s, can be easier to find that mirror plane than the 1,3s or the 1,4s. So, okay. So let's just look at how many different stereocenters we can find. Remember, the first thing we need to look for is how many things are bonded to each carbon. So if we look at this one right here, we need to remember we have hydrogen right here, and we need to remember they need to be different groups, okay? So if we're thinking about different groups, we want to think about that prioritization system, right? Because this is a carbon, and this is a carbon. So They're all the same group. Well, not really, because this carbon has a carbon and a hydrogen attached to it. This carbon has a hydrogen and a hydrogen and a hydrogen attached to it. This carbon has a carbon, and a carbon and a hydrogen attached. But moving with our prioritization down to the next one over, we see a differentiation. That carbon has an oxygen on it, giving that side higher priority. So we have 4 different groups attached to this, so that makes this a stereocenter or a chiral carbon. Okay, let's find some more right here. So just quickly, this one's not a chiral carbon. This one's not a chiral carbon because we have 2 hydrogens, 2 hydrogens, 2 hydrogens. So we can skip all of those. This has 2 methyl groups on it, so we can skip that one. So we have 2 carbons left to figure out. And in this one, we get differentiation here because this is a carbon and 2 hydrogens. And this is a carbon with an oxygen and a hydrogen. So that makes this not only the higher priority, but also a chiral carbon. Makes this the chiral carbon because this has a carbon and a carbon. So do we see how we look for those 4 different groups attached? Okay. And don't forget, I didn't draw the hydrogens on any of those, so that hydrogen counts as our 4th group. Okay, now, drawn in this configuration, we actually can't tell what isomer it is because we don't have enough information. We will not have enough information about which actual isomer it is until we draw the wedges. Because with it like this, the hydrogen could be above or below the plane. We don't know. So in the case of the wedging system here, with our wedge fishing out like this, we know our hydrogen is now back, and that helps us assign priority. And in this one, we know our hydrogen is back, which helps us assign priority. And we know our hydrogen is forward, which helps us assign priority. Okay. Now, when we assign the priority to these, we do the same thing. We put our one in the back and do 1, 2, 3 clockwise R, 1, 2, 3 clockwise R, and 1, 2, 3 counterclockwise, giving us S. Okay. All right. All right. So what if you had more of the 3 or more stereocenters? Okay. So in this particular compound here, this is cholesterol. We can end up counting 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's 2 to the 8th number of isomers possible. That's 256 possible stereoisomers available to us. Okay, but the body only makes 1 isomer. Okay, and it only metabolizes, this is the one that we actually use in our bodies right here. And it only has 1 possible use in the body and only 1 possible isomer the way it's made. Okay, so why? Okay, it's done that way because chirality makes it fit into enzymes in different ways. There's only 1 pocket for this enzyme to fit in, and I'll talk about that toward the end. But so it has 1 pocket, 1 way to fit in it. So if these molecules only differ by how they are in space, how can we tell them apart? You know, we only know R and S because we drew it. You know, how do we tell them apart in the lab? How do we say this one's R and this one's S? Okay. Well, it turns out because we have 4 different groups here, they interact with light differently. Okay. And we have what we call optical activity. Okay. So ordinary light is, just electromagnetic waves, right? It has an electronic component and a magnetic component. Okay. If you have light coming from the sun, it's going in, that wave is going in a particular direction, and then there's another piece of light coming with another direction. And so they're all randomly going around and they're all kind of going in the same direction. Okay. But if we take that and filter out all the ones that aren't going in the same direction, we can call that plane polarized light. All of the waves coming through there are going in that same parallel direction. We still have lots of beams of light coming through, but they're all together. Okay. The cool thing is we can tell if something's chiral or not by how it interacts with this plane polarized light by using a device called a polarimeter, which we're going to put light that's plane polarized like this. We're going to put an optically active material, which is something that interacts with that light. And what we'll see is as the light passes through the polarimeter, it's going to change the plane in which that light is in. So that light is interacting with the chiral molecules and slowly rotating around to give us. And the amount it rotates tell us it's optical activity. And that's how we tell the difference between different chiral compounds. Okay, so polarimeter is actually a very easy device. You have a light source, you have a polarizing film, you know, just like you ever had like a pair of sunglasses that were polarized and you put them, you tilted one 90 degrees off the other and it goes black. Well, that's what plane polarized light does, that all the light coming through one of them was going this way. And because the filter was in the other direction, it couldn't go through. So in this case, we're lining it all up on one plane. Then we're shooting that light through a sample. Usually it's about 10 centimeters long. And then we measure how much the light has rotated by the time it gets to the end of the sample. Okay, and that light that gets at the end of the sample is what we call our optical activity. And so we're going to have a positive or a negative change in the polarized light. Okay, so if our light is rotated clockwise, it's called Dextro Rotatory. Okay, and so a lot of compounds will see in, especially biological systems, they'll have a D or an L in front of them because the D or the L tells us which way the plane polarized light is going to be operating. Okay, lava rotatory is when it tilts the light counterclockwise. Okay, so, well, that's counterclockwise for me, but so if one is going positive and one is going negative, that means that an optical activity of a substance, one of your isomers, your R or your S, is going to rotate the light dextrorotatory. The other isomer is going to go in the equal and opposite direction the other way. Okay, so R is not always dextrorotatory or laboratory. S is not always dextro or laboratory. You just don't know. You have to be able to measure them some other way to know the stereoisomer. And then you can actually measure them. And notice that when we do, one will go positive a certain number of degrees, the opposite isomer will go negative a certain amount of degrees. Okay. Now, to make sure everybody's measuring this the same way, we have what we call specific rotation, where we take an exact concentration, which is 1 gram per 100 milliliters, a certain length of tube, usually 10 centimeters, and where we can use or you can use the pure liquid if you use it as grams per milliliter. Now, that gives us this little symbol in front of it now. So the alpha is the optical activity. So alpha for activity, bracket 25 tells you the temperature you measured at, because it changes slightly if you measure at different temperatures. D tells you that it was actually a sodium D line, so you're measuring a specific wavelength of light in your plane polarized line as well. Okay. So when we name these, we have to go, let's name them. So we have our hydrogen back, our OH, our 1, 2, and 3, that is counterclockwise, so that's our S. We have to say that it rotates light in the positive direction. So S dash plus 2-butanol. And then the opposite isomer is going to be the R dash minus 2-butanol. So that's kind of what those, if you see that extra little bit of information in a lab report or something, that's what it means. So the positive is going to be dextrorotatory, the negative is laborotatory. Okay, so except for inorganic salts and some very low molecular weight systems, there's a lot of things that are chiral out there. Chiral carbons, chiral nitrogens, chiral sulfurs, and most biological systems have many chiral molecules in them, and they almost always use one of the stereoisomers. Okay, almost always. In some cases, you'll actually see a lot of the sugars are all going to be labeled L because they're all going to be laboratory because they're all going to have that one specific form or the other. So, and the whole reason for that is that enzymes are like very precise chemical engines, okay? So it's a protein that has little pockets on the side, and each little pocket does one thing and one thing only. So if you have this pocket, and so it has to fit in that pocket exactly right, okay? So these enzymes are used all over the body for everything. This particular enzyme has 251 stereocenters, which means that's going to be millions of possible stereoisomers, okay? But the body only makes one. And that one does a very good job at creating those, that chemical engine that creates only that one stereoisomer to be produced and used, okay? So let me kind of give you a visual on why. So on our enzyme, it's a very big molecule. It's big and lumpy and has all these different little places that go into it. But when a molecule is coming up to the enzyme to interact with it, it has to fit in a certain way. Like the oxygen and hydrogen can fit in one slot, a hydrogen or maybe an aldehyde can fit in another slot, and a different OH can fit in another slot. So it has to fit in exactly right. And so in this case here, we have the aldehyde looking like a square peg, and we have our OH looking like a round hole. And so that means that only that R isomer will fit in that pocket. If we swapped the aldehyde and the alcohol, that alcohol does not fit in that square hole. It's a round peg in that square hole and will not fit, and therefore it does not bind. If it does not bind, it cannot interact with the enzyme and it cannot be processed by the body. Okay. Question on enzymes. Okay. So let's go back to our naproxen again, okay? We saw that the S was the active one and the R is inactive for that system, okay? So in contrast, even, and similarly, naproxen, which is related to it, is a good pain reliever. It's all sold as Advil, I believe. And only the S isomer is actually used as a pain reliever as a non-steroidal anti-inflammatory agent. However, the R isomer happens to be very bad for the liver. It's very, very toxic to the liver because only the liver can process it. It creates a bunch of formaldehyde and other byproducts that are really bad. So in the case of ibuprofen, it's just inactive, okay? But in the case of naproxen, they actually have to make one isomer and one isomer only and make sure they remove all that other isomer if they do make it, or else they will cause liver damage. Okay. So if we have R and S, and we know that if we have a pure R, it'll rotate light one way, and the pure S is going to rotate it equal and opposite the other way, what happens if we have mixtures? Okay. So if we have mixtures right there, so we can have a equally, 100 molecules of this and 100 molecules of that. And if we tried to take the polarimetry experiment and measure the optical activity, the 100 molecules here would rotate it this way, and the 100 molecules here would rotate it this way, and it would turn to 0. So that's how we know we have an equimolar mixture of two enantiomers, okay? So we would do that. So before we saw it was very important to not have the two different isomers of naproxen in our system. We wanted only one. So how do we separate these mixtures that we have if they have all the same properties? They have all the same boiling point, melting points, everything's the same except for that fixed in space place, okay? So the best way to do it is to use enzymes, because enzymes are very specific about how things fit into this pocket, okay? So the way they actually resolve this for naproxen is they turn that carboxylic acid into an ester. And when they do, they actually make the process. And then they use a specific enzyme that will only interact with the S. Only that S ester can fit in that pocket, and clip off that, that ester group, that ethyl group that's here, giving us that free naproxen. That free naproxen can be separated from the R isomer because now they're different compounds. One has a carboxylic acid, one's an ester. They have different physical properties. They can be separated. Okay, so enzymes are really good in our bodies, and they're really good for the production of our pharmaceuticals as well. Okay, so let's talk about this. Okay, in chapter 5, we learned that we could add water across a double bond. And we learned when we added water across a double bond with acid, we would end up getting the hydroxide to be on the more substituted carbon following our Markovnikov rule, and we'd have that secondary alcohol when we make it. Okay, so because we're going through that, but because we're doing that in that method, we're forming a carbocation or a contact from either side. So it's going to give us 2 isomers. Okay. So the first thing I want to know is butene chiral? Are there any carbons on butene that have 4 different groups bonded to it? Okay. So I'm going to say no, because we have 2 hydrogens, we have a hydrogen and a carbon, and then another carbon here. So only things with 4 other things attached. So nothing on the alkene can be chiral. And that has 2 hydrogens, this has 3 hydrogens. So butene itself is not chiral, right? When we make the butanol, we now have an option here, because just drawing as it is, it doesn't show us any stereochemistry. So because we're going through that carbocation intermediate, we can have it come, the water add to the top or the bottom. So that means that we're going to get one isomer that is going to be the wedge out, and the other isomer is going to be the wedge in. Okay. So because these are now non-superimposable, because if you rotated it around and try to superimpose, it wouldn't superimpose, we now know that the 2-butanol is actually a chiral. Okay. And now, how many different stereocenters do we have on this now? Well, we only have 1 carbon with 3 different groups, so we have 1 stereocenter. And because we're going through that carbocation intermediate, it's going to be half one, half the other. And so we're going to end up with an optically inactive mixture until we find a way to separate them, either enzymatically or some other way to separate them. Okay. All right, questions about chirality. So optical activity tells us that we do have pure optical compounds. If we actually mix them together in different proportions, we would have either some plus or minus, but if they're equal portions, optical activity drops to 0. Okay. If it's not already there, I'm going to upload an activity just for practice to help assign RNS. Now, on this page, there are going to be things that are not chiral. So the first thing you look for is 4 different groups. Then you assign prioritization to it. And then once you have assigned priority to it, you can assign RNS based on the clockwise or counterclockwise. And it's not for grade, it's just for fun. It's just so you can have some practice doing it. Okay?
Is that under files or
let me double check. I will look for that right now. Let's see, files. It might already be there. I think I might have to upload it. If it's going to be there, it's not under files yet, but the nomenclature review with the rules is. Is it under activities? It'll be under activities. Oh, yes, it's already there. It's under activities, it's class activity 1. Okay, so on the first page, you figure out what's chiral and you assign chirality to it. On the second page, you get practice drawing the enantiomer or the mirror image of it and then seeing if it is an enantiomer or not. Okay, so that way you can do this. So here, let me pull it up actually. Let me share my other screen. So it's under activity And it's not for grade, it's just for fun. Google Files, there we go. Okay, so this is under, let me just go back real quick. So it's under our web page, it's under activities, class activity 1. The first page here is a number of different structures here. Now notice on these ones right here, the ones that are have multiple carbons in them, only one of those carbons has a stereocenter. So you're only going to assign one stereocenter. You have to figure out which ones has the stereocenter, or is chiral, and then assign it. Okay. Let's see, we have a lot of these with this nitrogen over here, and so that's just going to help you with your prioritization. Notice some of these have double bonds to carbon here that you might have to draw out to make sure you get your prioritization right. And then the second page is draw the enantiomer. So draw your imaginary plane and get your wedges and your substituents on the other side. So what I'll do is I'll go ahead and post the key to this, and you can use it as a study guide for getting this right-handedness and left-handedness down. Okay, questions on that?
I have a general question kind of about the exam. What will we have available to us? Do we get to use a periodic table or scratch paper or anything like that?
Yes, I'm going to send an email out about that. There is a periodic table that's our departmentally approved periodic table is at the beginning and end of the exam. So you have that with you on Top Hat. Okay, so you don't need one yourself. That way I know everybody's using the exact same periodic table. Number 2, you may use 2 pieces of scratch paper, but you have to show them to me before and after the exam on the Top Hat Proctorio app. Okay, and when we do have the exam, you don't come to class, you don't come to Zoom, you go straight to Top Hat. You'll have one exam assigned to you. You go ahead and open it, follow the instructions, and go ahead and take it. Starting next week, I'm going to open up a mock exam so that you can practice logging in and using all the different tools that you have available to you, and so that you can get comfortable with the process of taking the exam on Proctorio. Okay? And again, it's going to be multiple choice. It's going to be similar in structure to what the homework is. It's just going to be different questions.
Do we have a review for the test?
Yes, the review is scheduled for Tuesday. We're going to go over all 7 chapters we've covered. And there's also a review posted under resources right here. Chapters 1 through 7, organic review. And so it's kind of going sort of in line with the chapters, but what are the big things that are important? Like, you know, hybridization. That's really important because it controls the shape of the molecule and it controls the acidity of the molecule. Acid and base theory, you know, how to tell the difference between all of them. The nomenclature rules. This is where you can do RNS and E and Z. And then let's see, it goes up to reaction mechanisms, stereochemistry, and then those reactions we started, the substitution reactions and the elimination reactions, and then a summary right here. This I don't think is actually in your slides, but that kind of summarizes all of our reactions we have. So that's all available to you to start studying now if you wish. And this is what I'll be going over on Tuesday. So if you bring questions, I can help answer them.
I didn't see anything about like chair confirmations and stuff that I remember on the study guide. Is that something we need to really worry about for this first exam?
No, because I mean, really the chair confirmation, you just want your largest group out to the side, you know, on the equatorial. That's the knowing that those are the more stable, I think is the most important factor with that.
Okay.
All right. We're right here at 12:19. So if anybody has any questions, we have a couple minutes here, and then I can, I'll go ahead and stop recording so that you can ask questions.